An air-gapped network is defined by its complete physical separation from the public internet. In operational technology and intelligence sectors, the prevailing assumption is that severing the network cable guarantees data isolation. But computation is an inherently physical process. Computer hardware constantly interacts with the physical environment of the room it sits in, regardless of network connectivity. Everyday components, from memory sticks to LCD monitors, continuously emit microscopic electromagnetic radiation and high-frequency acoustic noise as they draw power and process data. Specialized malware can weaponize these microscopic byproducts, converting them into covert, out-of-band communication channels. Two distinct physics-based methods demonstrate this capability: the Rambo attack, which broadcasts radio waves from memory architecture, and the pixel attack, which forces screen pixels to generate sound. Neutralizing these threats requires transitioning from logical network security toward the rigorous physical containment standards found in CIF and Tempest engineering. Trusting a severed Ethernet cable to protect highly classified data is a dangerous architectural blind spot. The historical precedent for breaching an air gap was set at the Natanz uranium enrichment facility in Iran, targeted by the Stuxnet worm. Stuxnet was part of a highly classified intelligence program initiated under the Bush administration. The operation's scope and deployment continued during the subsequent Obama administration. The primary infection vector bypassed the network entirely. The malware was physically carried into the facility's perimeter on weaponized USB drives. Once inside, the Stuxnet payload specifically targeted programmable logic controllers, the industrial computers automating the facility's centrifuges. The code systematically destroyed the electromechanical equipment while simultaneously feeding false, normal baseline feedback to the main controllers, blinding the operators to the sabotage. While these infected drives were effective, they represent the first generation of physical air-gap bridging. The success of Stuxnet shows that human error and removable media render a physically isolated perimeter inherently porous. Once the perimeter is compromised, the attacker faces the secondary challenge of extracting stolen data out of the isolated machine. The Rambo attack achieves this by exploiting the physics of memory hardware. As data transfers across RAM buses, rapid voltage changes radiate invisible radio frequency emissions. Malware manipulates these using memory commands like the MOVNTI instruction to dictate electrical current timing, creating controlled rhythmic bursts. This technique functionally turns the computer's standard memory architecture into a makeshift radio transmitter. This oscilloscope screen shows the raw waveforms generated by the hardware. To transmit data, the malware modulates the signal using on-off keying, where the presence of a wave dictates a binary state and its absence dictates another. Attackers rely on Manchester encoding, shown here on the bottom. This method forces a consistent number of signal transitions, synchronizing the clock between sender and receiver. Pushing encoded data across a RAM bus achieves transmission speeds of 1,000 bits per second. At this speed, a 4096-bit RSA encryption key can be leaked through a physical wall in roughly 4 seconds. When compromised by specialized malware, standard computing hardware operates like dedicated radio broadcasting equipment. Highly secure environments actively monitor for these radio anomalies and physically remove all audio hardware to enforce a strict audio gap. The pixel attack defeats this by weaponizing the LCD screen itself to produce sound. Malware forces the display to generate specific, low-brightness pixel patterns. Every rapid transition in pixel state forces microscopic capacitors and electrical coils within the monitor to physically vibrate. As this overlaid frequency chart shows, these rapid capacitor vibrations generate precise acoustic signals squarely within the 0 to 22 kHz band. These acoustic emanations are often entirely imperceptible to the human ear, but they are easily captured and decoded by a nearby receiving device. This method provides a clear stealth advantage. The screen can appear entirely black to the naked eye, while the display actively transmits data. Textual and binary data can be successfully exfiltrated from the isolated machine up to 2 meters away using this acoustic method. Any hardware component drawing power and changing state is a potential acoustic vector. Simply removing the speakers fails to address the physics of the machine. Mitigating these out-of-band threats requires strict adherence to physical containment specifications, precisely outlined in the CNSSM, Tempest, and ICD 705 engineering standards. The foundational principle of these facilities is red-black separation, a structural division isolating classified red systems from unclassified black systems. The layout mandates rigorous spacing. A physical 1-meter separation must be maintained between any red equipment and black wiring to prevent signal crossover. To explicitly mitigate radio frequency threats like the Rambo attack, sensitive compartmentally information facilities construct comprehensive Faraday cages. These enclosures require continuous copper foil or welded steel panels, properly grounded, to contain all errant electromagnetic radiation. Defeating acoustic channels like Pixhel requires facilities to enforce a sound transmission class rating of 50 or higher. Achieving this acoustic rating dictates construction materials, multiple layers of dissimilar mass, heavy-gauge steel doors, and perimeter neoprene seals to block all physical vibrations. Even the facility's HVAC ductwork must be aggressively baffled with sound-absorbent materials, so the ventilation system cannot act as a conduit for acoustic waves. To counter modern covert channels, security professionals must treat the physical facility itself as the primary containment layer for hardware. The mental model of a secure network must evolve. A severed Ethernet cable provides zero defense against hardware emanations. Computation requires moving electrons, and those electrons inherently produce electromagnetic and acoustic signatures. Methods like Rambo and Pixhel prove that attackers are bypassing software vulnerabilities entirely to exploit the microscopic physics of the hardware itself. Protecting isolated data demands rigorous physical construction standards, continuous RF monitoring, and the strict application of zero-trust principles. Maintaining a functional air gap is a rigorous physical engineering challenge.